Alright, Chapter 5, Analytic Trigonometry. Analytic trigonometry, the reason it's called analytic trigonometry and not just regular old trigonometry like Chapter 4, is that you're going to notice that in this chapter there's a lot more algebra-based problems. For instance, the first real main topic in this chapter is going to be verifying trigonometric identities, which is really just the same thing that you did back in Algebra 1 where really it's a combination of Algebra 1 and Geometry, where we're going to take some algebraic equations, or trigonometric equations, and prove them to be true. We're also going to look at solving trigonometric equations, which is going to bring us back to unit circle type problems. And then the second half of the chapter is really just formula-based, where you're going to be given a special formula that has to do with trigonometry, and it's essentially just plug and chug. Now, before we get into any of that, just like with Chapter 4, where you had to memorize the unit circle, anything in Chapter 4 had everything to do with the unit circle. You had to know the unit circle in order to be able to do anything in Chapter 4. Now again, unit circle's not going away. It's going to be coming back up in this chapter. But the foundation of Chapter 4 was the unit circle. The foundation of Chapter 5, on the other hand, is the fundamental trig identities. Alright, the fundamental trig identities are so named because they are so commonly used. There are 5 sets of fundamental identities that we're going to be looking at. Now, there are more than just these 5 sets of identities, but these 5 are commonly referred to as the fundamental identities because, again, they are so commonly used, and because they are so commonly used, you need to memorize them. Do whatever you need to do in order to memorize them. You can't move on in this chapter until you have memorized them. Good news is some of you already know. For example, the reciprocal and the quotient identities, you may not realize that you know them because the name may not be as familiar with, you may not be as familiar with the name, but you know these identities. The reciprocals and the quotients, you've already got those memorized. We've been using them all through Chapter 4. The ones you don't know yet, but you'll learn to know and love very, very soon, the Pythagorean identities, the cofunction identities, and the even-odd identities. Altogether, there's going to be 23 of them. 23 fundamental identities that you need to have memorized before you move on to the next section. Good news is that they're not that difficult. They have very much to do with each other, and they follow patterns, which makes them very easy to memorize. So let's start going through them. But before we do that, let's clarify what I mean by an identity. Now, in algebra, an identity is an equation that is true for all values within its domain. Now, as we go through this video, occasionally I may pause, like I may ask a question and then I'll pause for just a second and then keep talking. The intention is that when I ask a question, I want you to pause the video and think about the answer to that question before playing it again to hear what my answer is. Now, if we had done this in class, I would be able to poke and prod to get the right answer out of you. But this is a video. I don't know who's watching this. There might be somebody right behind you right now, and you don't even know. When I pause, feel free to pause the video or rewind or whatever you want to do. It's a video. It's up to you. I don't know what you're doing. Okay, enjoy. An identity is an equation that is true for all values within its domain, as opposed to an equation that's not classified as an identity is any equation that is true for only specific solutions. In other words, all equations have solutions. The question is, how many solutions do they have? An identity has infinite solutions. If it's not an identity, it only has 1 or 2 or 3 or a certain specific number of solutions. All right? Here's an identity. X squared minus 1 over x plus 1 equals x minus 1. Versus, here's not an identity. In other words, this one's just a random old equation, nothing special about it. X squared minus 1 over x plus 1 equals 0. Let me show you why this one is an identity and this one is not. All right? Let me get my writing tool. All right. Now, either one of these I could solve using the same techniques. Step 1 is to multiply the denominator to the other side. In other words, set this over 1 and cross multiply. All right, well, over here, when I cross multiply x plus 1 times x minus 1, well, hey, that's just like a plus b, a minus b. That's the difference of squares. If I FOIL this out, x times x is x squared. X times negative 1 and positive 1 times x cancels out. Positive 1 times negative 1 is just negative 1. So the right side is x squared minus 1, and that leaves on the left side x squared minus 1. In other words, if it's an identity, when you attempt to solve it, the left and right side are going to be exactly the same. We've got the same thing on both sides, so no matter what number I plug in for x, it will always be true, except, of course, keep in mind the domain of the original function, x could not equal negative 1. So even though I could plug in negative 1 here, negative 1 is not in the domain of the original one, but that doesn't really matter. What matters is that within the domain of the original problem, which was all real numbers except x can't equal negative 1, I can plug in any number I want to and it would work. Versus over here, that's not going to work. I could plug in any number I wanted to, but that doesn't mean it's going to work. The only ones that are going to work are the ones that are solutions. Well, if I cross multiply on this one, I get x squared minus 1 equals 0. And when I finish solving that up, it's going to be x equals positive negative 1. But of course, negative 1, not in the domain. So there's only one solution on this one, x equals 1. Now, it could have 2 solutions. It could have 47 solutions. The point is, though, it doesn't have every possible solution. An identity has to have every possible solution it could possibly have. A regular old equation only has specific solutions. All right? Not an identity is an identity. All right? Now, in the next lesson, we're going to talk about how do we go about verifying that something is an identity. What we did right here is one possible technique for verifying an identity, the fact that I tried to solve it and I got a statement that was 100% and always true. The left side is always equal to the right side, as opposed to over here, x squared minus 1 doesn't always have to equal 0. It could have just as easily equaled some other random number that I happen to have picked. All right, but we'll talk about that more in the next lesson. This lesson, we want to address what the identities are. So here's my first list, the reciprocal identities. Again, remember how I said some of the identities you already know? You already know these identities. You should already know these identities. We've been using these identities for about a month and a half now. We know that sine is the reciprocal of cosecant, so that means that sine equals 1 over cosecant, and likewise cosecant equals 1 over sine. Cosine equals 1 over secant, secant equals 1 over cosine. Tangent equals 1 over cotangent, cotangent equals 1 over tangent. So as long as you know that the reciprocal of sine is cosecant, well, then you have two identities memorized right there. Sine is 1 over cosecant, cosecant is 1 over sine. Simply by knowing the relationship between sine and cosecant, there's two identities memorized. As long as you know the other two, well, then you have all 6 of these identities memorized. The next pair that you already know, again, another pair that we've been using all along, the quotient or the tangent identities. Tangent is sine over cosine, and cotangent is cosine over sine. As long as you know that the relationship between tangent, sine, and cosine is that sine divided by cosine is tangent, and if you know that, well, tangent and cotangent are reciprocals of each other, if you know this one, then you automatically know this one as well. Now, let's talk about exponents real quick before we talk about the next set of identities and how we write exponents. We've started talking about this a little bit when we started talking about inverse functions, but now we need to be a little bit more specific because when it comes to trig, you got to be careful when you write an exponent. For instance, here's the cosine ratio. Now, it doesn't have to be a cosine ratio. It could be any ratio you want: sine, cosine, tangent, secant, cosecant, cotangent. Well, what if I want to square that quantity? I could always write it like this. All right, I take the cosine function and I square the entire function. But kind of a shorthand when we're doing trig, instead of having to write those parentheses, it's quite common. It's actually more common. Instead of writing it like this, we write it like this. In other words, the square applies to the entire cosine function. Or I can put the 2 right here, and again, it applies to the entire cosine function. These two statements say exactly the same thing. If I see this, I need to think this. In other words, if I plugged in a number for theta, I don't square the word cosine. That makes no sense. I evaluate the cosine at that angle and then square that answer. In other words, just like this. I do not square the angle and then take the cosine of it. These are not the same. This is not the same thing as these top two. Don't square the angle, square the answer to the cosine ratio. All right? So again, these two say the same thing. I can do it with a square, a cube, a fifth power, a sixth power. I can even do it with negative exponents, except for -1. You cannot use this notation. So here's the one little facet about this notation. You can use it for any number you want, for any exponent you want, but you cannot use it for -1. And hopefully you realize why you can't use it for -1. On this one, this says square the cosine ratio. Square the cosine ratio. This one says to the -1, which of course means reciprocal. 1 over cosine is what that literally says. But over here, that -1, think about it, think about it, think about it. What does that cosine to the -1 mean? Of course, that's an inverse. Not a reciprocal. That is not an exponent. That is a label. All right? When I have it written like that, that specifically means inverse cosine. So -1 is the only little thing that you got to worry about when you're using this notation. You can do it with any other number. You can take that exponent and put it right here for any number, as long as it's not -1, because then it overlaps with a separate notation that means something different. Okay? So let's talk about the Pythagorean identities. All right, and the Pythagorean identities are so named because, of course, they have to do with the Pythagorean theorem, a squared plus b squared equals c squared. So then you might be saying, Mr. Scholar, if you're talking about the Pythagorean identities or the Pythagorean theorem, why do you have a circle drawn right there? And I'll say, shh, quiet. Of course it's a triangle. Triangle's right here. If I just take a circle, draw a radius in. Now, this doesn't have to be a unit circle. It could be any circle whatsoever. Draw a circle with radius r. All right, again, not a unit circle. If it was a unit circle, it would be radius 1. That's too specific. I'm doing this in general. This works for any circle. Radius r, and then drop an altitude. All right, so radius r connects at the circle at the coordinate x, y. Drop an altitude from that coordinate. There's y. In other words, the height of the triangle is y. In other words, the y value of the coordinate. And then this length right here would be x. So there's your right triangle. Stop your whining. So of course we know this is a right triangle, and we know the Pythagorean theorem says that a squared plus b squared equals c squared. So then I could really just say x squared plus y squared equals r squared. A, B, C. A, B, C. All right. Now I also happen to know, because of my knowledge of trigonometry, that I can also pull out some trig ratios here. For example, the cosine of theta would be x over r. And before I pull out another one, I'm going to realize, hey, can't I take that r and move it up here? Sure I can. Multiply both sides by r, you get x equals r cosine theta. I can do the same thing with my sine ratio. Move the r upstairs, y equals r sine theta. Now you might, at this point, start to realize what we're actually going to do. X squared plus y squared equals r squared. Well, here's what x equals. We're going to take that and plug it in right here. Here's what y equals. We're going to take that and plug it in for y. In other words, r cosine theta squared plus r sine theta squared equals r squared. I took the x, set what x was equal to, plugged it in for x, put it right here, did the same thing for y. Now we can keep going, clean this up. When I have two quantities being multiplied together, in other words, ab squared, that really says a squared b squared. So in other words, I can take those exponents, bring them inside the parentheses as r squared cosine squared, r squared sine squared, and of course this other r squared just comes straight down. And since everyone has an r squared, if everybody's special, then no one's special. We can get rid of all those r squareds. It leaves a 1 behind over here. and we have this statement right here. This statement is the statement that you need to remember. Cosine squared plus sine squared equals 1. This is probably one of the most useful identities that's going to come up in this chapter and throughout the remainder of the course. Cosine squared plus sine squared equals 1. Now, doesn't matter which one comes first. It's an addition problem. Sometimes I'll write it sine squared plus cosine squared. Sometimes cosine squared plus sine squared. It never matters. That is your first Pythagorean identity. Now, there are two more Pythagorean identities, but they're based on this one as well as by using reciprocal and quotient identities in combination with this one. For example, let's say I took all three of those terms and just for kicks, divided everything by cosine squared. What would that do? Well, cosine squared divided by cosine squared is, of course, 1. Sine squared divided by cosine squared, well, there's our tangent identity. Sine over cosine is tangent. Therefore, sine squared over cosine squared would have to be tangent squared. 1 over cosine squared, well, 1 over cosine is secant. 1 over cosine squared would be secant squared. So there's our second Pythagorean identity. Cosine squared plus sine squared equals 1. 1 plus tangent squared equals secant squared. Now, to get our third identity, hopefully you can kind of realize what we're about to do. We'll go back to that original Pythagorean identity, but this time, what are we going to divide by? We're going to divide by sine squared. Cosine over sine is cotangent. Sine over sine is 1. 1 over sine is cosecant. And of course, still having the squares in there. All right, so here are our three Pythagorean identities. Now notice the patterns. First one, the primary one, cosine squared plus sine squared. We'll put those cosines and sines together. In other words, x squared plus y squared equals r squared. All right, on the other two, we've got 1 plus tan equals secant. Cotan plus 1 equals cosecant. All right, the cos go together. The not cos go together. Secant and cosecant always stand alone by themselves. Tangent and cotangent, they need buddies, so they hang out with the ones. All right. Again, it doesn't matter what order you write the additions in. If you want to always be consistent and write 1 plus tangent squared, 1 plus cotangent squared, that's perfectly fine. All right. Many different ways you could see these Pythagorean identities written, but these are the main ways you would see them written. If I ask you, hey, what are the Pythagorean identities? These are the three formats that I expect to see. But again, be prepared to see them in alternative forms. In other words, be prepared to see them with one of the terms moved to the other side. For example, these two are the exact same as this one. On this one, all I did was I took the cosine squared, subtracted cosine squared from both sides, canceled on the left. Now I have 1 minus cosine squared on the right. Same thing with the second one. I have 1 minus sine squared instead of cosine squared plus sine squared. All right, so in other words, you can just take any of these two terms, move it to the other side with subtraction. Be prepared to see 1 minus cosine squared, 1 minus sine squared, or secant squared minus tangent squared, secant squared minus 1, cosecant squared minus cotangent squared, cosecant squared minus 1. Be prepared to see these alternative forms of the Pythagorean identities. But again, if I ask you what the Pythagorean identities are, it's just these three. Cofunction identities. All right, so the cofunction identities, as long as you can remember sine and put a co in front of it to get the cofunction, then you have the cofunction identities. All right, sine of A. What's the sine of A? Well, based on this triangle, if A is right here, sine of A would be y over r. Well, what if I asked you cosine of B? In other words, Dr. Huxtable. I'll just let that sink in, and if you don't get it, that's your problem. Cosine of B. Well, cosine of B, here's angle B, adjacent over hypotenuse, would also be y over r. So in other words, the sine of A and the cosine of B are equivalent. They will always be equivalent. In other words, the trig function of one angle will always equal the cotrig function of the other angle. The reason for that is the relationship between A and B. A plus B equals pi over 2. In other words, in degrees, angle A plus angle B will always equal 90 degrees. If this is a right triangle, A and B always have to equal 90 degrees. Again, pi over 2. In other words, in geometry terms, those angles are complementary. Complementary means they add to 90. If they add to 90, they are complementary. Co-complementary. Cofunction means functions that are complementary. All right? So sine and cosine are so named because cosine is the complement of sine. Now I could keep going. Since I know that a plus b equals pi over 2, I could rewrite this statement using only one angle. Instead of using both a and b, I can realize, well, a is just pi over 2 minus b, and then I can take pi over 2 minus b and plug it in right here. This right here is my cofunction identity. This is how cofunction identities are written. In other words, sine to cosine is just pi over 2 minus the angle. Or in graphing terms, you can think of that as a horizontal shift of pi over 2. If you think of the graph of sine and cosine, it's just a horizontal shift of pi over 2. And I can do that with all 6 pairs of the cofunctions. Sine and cosine are cofunctions, so I can write it either way. I can either put the shift on the sine, or I can put the shift on the cosine. It doesn't matter. If I see pi over 2 minus theta, that's a cofunction identity. I can replace with its cofunction. Tangent to cotangent, cotangent to tangent. Secant to cosecant, cosecant to secant. It doesn't matter. The last set is the even and odd identities. Way back in Chapter 1, we talked about even functions and odd functions. So I want to give a brief reminder on what I mean by even functions and odd functions. So for the function x squared, we can tell by the exponent this is an even function. Well, let's look what an even function looks like. Well, x squared is a parabola, and hopefully remember, even functions have y-axis symmetry. I've got it split right down the middle. That's supposed to be a straight line. Use your imagination. In other words, the right side and the left side are mirror images. If it's an even function, right side and left side will always be mirror images of each other. All right. In other words, if I pick a point right here, the corresponding point will be smack dab on the other side. All right. So this point is the coordinate xy. This point would be the coordinate negative x, y, but they would have the same y value. In other words, whether I'm looking at the function at the negative x or at the positive x, it's always going to have the same y value. In function notation, we would write it like this. In other words, the function value at the negative x and the function value at the positive x are exactly the same. So this right here kind of tells us what we can do with even functions. If it's an even function and I see a negative in there, well, I can just ignore that negative. If I have a negative number plugged into an even function, feel free to ignore the negative because you're going to get the same value as your answer, whether it's negative or not. If I plug in for x squared, if I plug in 2 or if I plug in negative 2, it don't matter. I'm going to get the same answer either way. If I plug in positive, who cares, and negative, who cares, just evaluate the positive one because the negative one's going to give you the same answer as the positive one. Odd functions, remember, if it's an odd number up here, that's an odd function. Graphically, odd functions not symmetric around the y-axis, not symmetric around the x-axis, symmetric around the origin. In other words, if I held this point steady, if I just held that point steady, I could rotate the graph around that point, rotate it 180 degrees, it would be right back to where it started. Alright? So in other words, if I pick a point up here, which has some coordinate xy, I could find another coordinate on an odd function simply by making both x and y negative. In other words, if I plug in a positive x, I get an answer for y. If I plug the negative version of that x, I don't get the same y, but I get the opposite of that y. In other words, the negative of that y. Function notation, we would say if I plug in a negative x for a function or a positive x for that function, I'm going to get the same value except they are going to be opposites of each other. So I could really put that negative either side, but this again points something out. For even functions, I can completely ignore the negative. For odd functions, I can take that negative and essentially pull it out of the function. I can pull it outside the function and then evaluate the function at the positive x. Now, to know among the trig functions which ones are even and odd, let's just look at the graphs. Here's sine, here's cosine. Now notice, which one of these graphs represents an even function, and which one represents an odd function? Remember that even functions are symmetric around the y-axis. Odd functions are symmetric around the origin, meaning you can rotate them and they'd be the same thing. Well, hopefully you've decided that the even function is, of course, the cosine function. Again, if I just split it down the middle, pretending this is a straight line, if I split it down the middle, the right side and the left side of the graph look exactly the same because cosine is an even function. On the other hand, sine, if I held it still right there and rotated the graph, I would end up being exactly the same. Rotating would get me an exact copy of the original graph. Sine is an odd function. Cosine even, sine odd. Well, what about tangent? Well, again, you can think of tangent from the graph. Well, hey, hopefully you can realize this one, it ain't going to be a flip. It's going to be a rotation. Tangent is an odd function. Tangent is an odd function. But you can also remember a trick that we did way back when. Tangent is really, by the quotient identities, sine divided by cosine. Well, if I take sine and divide by cosine, in other words, if I take an odd function and divide by an even function, what do I always get? Odd, think negative. Even, think positive. Negative divided by a positive is a negative. Odd divided by even is odd. So, even functions, cosine. So that means I can write it like this. If I plug in a negative angle to a cosine, feel free to just ignore that negative. Drop the negative completely. You don't need it. Now, I'm not going to go through the proof of why the other three are going to be true, but if cosine's even, secant is also going to be even. Sine is going to be an odd function. In other words, if I see a negative inside a sine function, feel free to take that negative, pull it to the outside, because sine is an odd function. Cosecant would have to be odd since sine is odd. And of course, tangent and cotangent would be odd as well. We saw why tangent was odd. Cotangent, if I take an odd function and flip it upside down, it's still an odd function. All right. Now, those are your 23 fundamental identities. You may not realize that we just went through 23, but there were 23 of them. Feel free to count it up. Memorize them, memorize them, memorize them. Whatever you need to do, you need to memorize them. If you don't memorize them, you're going to be in the same place that you were in the middle of Chapter 4 when you realized that you hadn't spent the time to memorize the unit circle and you had no idea what I was talking about in class, or you thought I was going too fast because I had the assumption that you had memorized it. I will not slow down if you don't memorize them, so you might as well memorize them. It's not hard, trust me. If I can do it, I won't finish that sentence because you'll just be upset with me. All right, have a good one.